Hello everyone. Today I'm going to present contactless infant monitoring using white noise. The last several years has seen increased adoption of smart speakers, including Amazon Echo, Google Home, Apple Pod, and so on. So the question we ask is, can we use smart speakers to monitor infants? Traditional solutions uses wired sensors that attach to the babies, which can lead to issues such as skin burning and choking. Instead, what we have is a smart speaker sitting in the bedside, continuously monitoring your infants, extending the functionality of ubiquitous smart speakers. In this talk, we will talk about the smart speaker solution to contactlessly track the respiration and motion of infants. The high-level idea is to transform the smart speaker into an active sonar system. A smart speaker is basically a multi-microphone array to pick up far-field voice and the speaker to emit sound. As a result, we can emit acoustic signal from the speaker and get reflected off the infant's body and received by the microphones, where we can analyze and extract the respiration and motion. So here is the naive solution. Let's just use a prior work that uses active sonar to track respiration. However, those work do not work for the following reasons. First, prior work uses 18 to 20 kilohertz higher frequency acoustic signals. The problem of that is the infants can not only hear those signals, but those frequencies can also cause serious issues such as headaches and nausea. Here's an audio clip of an FMCW signal in the audible range that you can hear what an infant could hear. I'm sorry. Clearly, it is so annoying. The second reason is that this prior work has a resolution that can only track adults but not for infants. Because for the infants, the reflection is much weaker, and the respiration rate of the infant is also much higher, which is like 30 to 60 breaths per minute, and that makes it even harder to extract the respiration. So instead, our solution is to use white noise on smart speakers to enable infants monitoring. The first thing we do is to use audible white noise, which is basically random signals. And the cool thing about it is that white noise machines is already the popular infant product, which is proven to improve their sleep of the infants, and many parents are already using it. The second aspect of the solution is to use smart speaker instead of smartphones. This allows us to leverage multiple microphones to do beamforming and to extract the weak respiration motion. So here are our contributions. We achieved the first contactless infant monitoring using smart speakers. To do this, we first utilized multiple microphones to localize the 3D location of the infant's chest. We then introduced efficient algorithms to extract weak respiration signals using beamforming. We evaluate our system using two different setups. We perform a number of micro benchmarks using an expensive infant simulator. We then deploy our system on 5 newborn infants to test our real-world performance. The first challenge to do this is to extract motion data from the white noise. The challenge here is all prior work used structured signals such as FMCW signal, or FDM packets, or simply single carrier waves. But white noise, in contrast, is by definition a pseudo-random signal. So our idea is as follows. As I mentioned earlier, we first used a speaker to transmit the pseudo-random white noise. The twist is, however, at the receiver side, we are going to transform the received random white noise signal into a structured FMCW signal. To see why this is possible, let's see what happens when you do. We'll take an FFT of the white noise signal. The spectrum has a flat amplitude, but what gives the white noise randomness is the phase of each frequency component. In contrast, if we see the spectrum on a whole FMCW chirp, we see that amplitude is also approximately flat, and we can approximate it as the same as white noise. But the difference, however, is the phase. It has the symmetric and deterministic shape, which is not random, and that's what gives FMCW its shape. So if we can adjust the phase of the white noise, the receiver can transform a white noise signal into a structured FMCW signal. So the whole pipeline is as follows. The speaker emits pseudo-randomly generated signal where the phase is known to us. We also calculate the delta phase of the FMCW signal and also the random white noise signal. The signal gets reflected back from the inference and received by the microphone. The microphone will take an FFT and then add the data phi to the phase of each frequency component. Finally, we obtain the transformed FMCW signal by doing an inverse FFT. The key is that we prove that in the paper that the transformation preserves multipath and motion information. And furthermore, now that we have the FMCW signal, we can apply the normal decoding algorithms to extract the location information. The second challenge we need to address now is how to extract the minute infant breathing motion. To appreciate this problem, let's play you a video of an infant and adult. They are breathing at the same time. As you can see, first, the size of the infant is much smaller, and secondly, the infant is breathing at a much higher rate. So to extract these minute and fast breathing motions, our solution is to utilize multiple microphones on the smart speaker to do acoustic beamforming. The speaker emits the sound, and we can add up the signal at the receiver side by the multiple microphones to boost the SNR. However, we first need to know the direction to beamform. One naive solution is to search the beamforming signal at array angles to find the angle that maximizes the respiration signal strength. However, this is computationally inefficient, as the search is linear to the number of angles and cannot run on a smart speaker in real time. What we designed in the paper is an efficient algorithm that maximizes the respiration signal strength in O log n times using ternary search, where n is the total number of angles in the search space. And we show that this can run in real time in a Raspberry Pi. Since commodity devices like Amazon Echo do not give us access to the microphone data, we built a smart speaker prototype using a cheap normal speaker and also a microphone array from Mini DSP, which has 7 embedded microphones. We first used a realistic infant simulator that are designed for the training doctors to practice infant-related operations. This consists of an anatomically realistic airway and supports various breathing features such as the breathing rate and intensity. We can even control the crying and motion of their arms and legs. We evaluate various parameters including distance, orientation, position, sound pressure, breathing rate, and interference. The key result we want to highlight is that our system works at a distance of up to 0.7 meter, and the error rate can be less than 10%. And it can detect up to 65 breaths per minute, and the result is not affected when the infant is wrapped with sleep sack. The second evaluation we did is with actual infants. We did it in the neonatal intensive care unit, or in NICU, in the UW Medical Center. The infants are kept in NICU because they are born immature, so they need to be monitored. And so we can use the monitor data as the ground truth to compare with the result of our system. We recruit 5 infants with the permission from their parents. The weight are between 3.5 to 4.5 kilograms and are less than 45 days old. We record a total of 218 minutes, and we manually label them into periods of moving, crying, and still. our algorithm can detect the respiration when the infant is still, and we see high correlation between our result and the ground truth. Moreover, we show that our system can achieve high accuracy on motion and crying detection as well. Finally, as a conclusion, here is a demo video of our smart speaker prototype monitoring sleep of one of our researchers' kids. You can see the waveform and you can hear a weak white noise signal. Okay, thank you very much, and I welcome questions.